lesson. Okay. So the first one was, okay, so fact one, let's go over this again, is that if you look at the circumcircle of the right triangle, the circumcircle of the right triangle, sorry. So let's do this. Okay, so if you look at the circumcircle of the triangle, right triangle, then the hypotenuse has to be the diameter. Well, sorry. Right? So because it's a circumcircle of the right triangle, so therefore this angle here must be a right, or rather say that because it's a right angle there, then this must be the diameter. Charles, how do you actually prove this? Because this is something which we know it must be true, right? You know that this is, if the center is if this point is a midpoint, then both sides are radius, and so therefore this radius. How do you actually prove that's the case?
So you're trying to, just to clarify, you're trying to prove that like the angle is a 90-degree angle or the radius?
Yeah. So usually you do this. You look at the circumcircle of this right triangle. We know there is a circumcircle. Do you agree?
Yeah.
Right. So suppose suppose you have a circumcircle there. Okay, like this. Now, if this were not, circle has to pass through these 3 points there. Okay, so like this. Now, you know, if this were not the, I shouldn't do this. If this were not the diameter, then we can draw a diameter from one point to somewhere, right? You agree?
Yeah.
Then let's look at this triangle again. Then using the inscribed angle theorem, we know that what? This angle must be a right angle, right?
Yeah.
And because these two angles are the same, so therefore this point must be the same as this point. This is called the unification method. Does that make sense to you, Charles?
Yeah.
So we draw a circumcircle, and then we say we draw the diameter from one vertex, and then we show that using inscribed angle theorem that the diameter must be coincide with this hypotenuse. Okay.
Yeah.
All right. So for the 30, 60, 90 right triangle, we look at the equilateral triangle first, and then we drop the altitude. Altitude has to bisect the base side, right, the bottom side. And therefore, because it's an angle bisector, right, the altitude is also angle bisector of the top angle. Therefore, the top angle here is 30 degree, and that's what you have. All right. What about factor 3? Factor 3 is that projection theorem of a right triangle, which we proved the last time. Do you agree? And factor 4, inscribed angle theorem, which we also proved in the class. Very good. How about number 1? Did anyone prove? Did anyone try number 1?
I did.
Okay. William, can you help us to discuss? Yeah.
Sure. Do I annotate on here?
Go ahead. Yeah, you can.
How do I enable it?
Click view options.
Go ahead.
You click view options and it should be on the bottom.
William, do you get it?
No.
Yeah, so Charles, can you tell William how you did?
So you just go to view options. Then once you click it, there should be like a select, like several options you could click. Then you just click annotate.
Is it like in video in settings?
So
You
you know how
just
there's like a green bar saying you are viewing blah 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 screen? It's to the right of that.
Yes, very good. Is that you writing? William, is that you writing?
Yes.
Okay. Talk. Explain while you are drawing.
Wait, I'm trying to unmute.
You are fine. You can talk. Yeah.
Wait. Okay. So here we also draw the midpoint, M. Of here. And then we also drop an altitude, CD. Okay, so the problem tells us that C is technically a right angle, and we have an altitude CD, while M is the midpoint of AB. And if MD equals CD, we need to find the degree measure of angle B. So clearly we can see here that this will be a 45, 90 degree triangle. So we can label this angle here.
So because we assume that this one equal to this one, agree?
Yeah.
Yeah.
So it's an isosceles right triangle.
CD equal to MD by assumption, right?
And since M is the midpoint of AB by fact 1 here, we can see that CM is also equal to AM and BM.
Right. Very
So
good.
we know that AMC is an isosceles triangle. So this angle here would be 135 degrees. And the two angles here would be they would be 22.5 degrees each. And this angle here would also be 45 degrees. And since all of these three angle measures, this angle, and this angle, they add up to 90 degrees. We can see that
We need to find this angle, but now this is it, right?
yeah, it's going to be 67.5 degrees.
Very good. Do you all see this? So you do have to use the factor 1, right? Without factor 1, it will be difficult to argue here. Very good. Do you all understand this proof? We do, right? And I want to say how many people actually solved this, this problem? A lot of people, right? Did you all try to work on this set? If you take a class without doing homework, you know that there's no way you can learn anything. Okay, so if you don't grab this opportunity, you will miss this topic completely forever. In other words, if you do not try to force yourself to get on top of this is a topic, then very quickly you're gonna get lost. All right, so there's no way you can keep going, you know, really understand Math Olympiad stuff without, you know, solving problems, you know, after each lesson. All right. So I do not collect your papers. I don't have that much time to grade your papers. It's too much extra work for me. But we do want to discuss those exercises in class so that you will get a pretty good idea. But listening to other people is not going to help you to master the topic because you only, just like you hand another lecture without doing exercise again. So it's not going to work out. Okay, so it's only after you tried solving them, or if you listen to other people, then either you feel very comfortable about it, or you would learn some new, some kind of a different angle of solving the same problem, right? Because you solved it maybe in different method, right? So the purpose of discussing it, it just give you a alternate view from other people, right? And for those people who didn't do the problem, what you can do is this. So you get a roughly pretty good idea how things are going. Then when you go home, try to resolve them again yourself. And if you didn't know how to solve them, but listening to people, then you get a pretty good idea. Then you can try to solve them yourself. And then that's a way to start, okay? So you might think that Math Olympiad is hard, but if you do this, you'll very quickly, you'll find that this is pretty easy to do, okay? All right, so let's move on to the next problem. Number 2. In the quadrilateral ABCD, which is the second graph in the page, angle B and D are 90 degrees, and angle A equals 60 degrees. AB equal to 4, and AD equal to 5. Let's find the BC over CD. So how do I find that? Yeah, go ahead. Anyone?
We're
Yeah.
gonna have to split
I like the lady to try first. Okay. What's your name again? I'm sorry.
Sorry, Grace.
Grace. Okay. Yes. Yeah. Great. If you can help us on this. Yes. Grace, could you try? Start.
Okay. So yeah, I drew the.
Let me draw this for you. Is
Yeah.
that okay?
Mm-hmm.
Because I think it's hard for you to draw.
Yeah.
So yes. Do you need a triangle in the end?
Hmm?
Do you need a triangle in the end, or you just want the quadrilateral?
I'll just the quadrilateral.
Quadrilateral. Okay. Very good. So let me just give you the quadrilateral. Okay, so this is going to be 4, 5, and this is right angle, this is right angle. This is ABCD. Okay, go ahead.
I don't know if I did like the best way. I'm pretty sure there's like a better way.
No. I mean, you see, we are not seeking for best way. Right now, whoever can solve it, as long as you can solve it, that's what matters. Okay.
Okay then. So this is the 60.
Right. Yes.
Right. So I kind of like drew a equilateral triangle. So this is 60.
That's cool. Yeah.
And this is 30.
Yes.
Right. So this would be 1, since 5. This would be 5.
Right. Yes.
And then this would be 2, and this would be square root 3.
Hold on. Where is the 2? Which one is 2? Oh, you mean this part?
Yeah.
This part. Very good. Yes.
Uh-huh.
Yes. Yes.
So,
So this is a 60. So this is 30, right?
mhm.
Very good.
And this is 120.
Right. 120 because it's a 30 degree here.
Uh-huh. And that's 30.
Isosceles, right?
Yeah, so this and this are same position. Yeah.
Yes. Yes.
Yeah, so that was kind of my main goal, to get them like, so this would be x. I turned it into x. I just wanted to get the two sides to be the same variable.
Right. Yes.
Plug
Yes.
in the
Yeah.
equation, right? So then this is x, and this is x plus square root 3.
Yeah.
Okay. So then I kind of just,
So DC over CB equal to x over x plus square root 3. Very good.
and then I just solved for I just solved.
How do you solve for x then?
So
Don't forget that you have this part here, right?
yeah.
What is that part? Let me call this point as a point E there.
Okay.
A, B, C, D, E here. Now what is DE?
Okay, so yeah, okay, now I know what I did. So both of these are 90 degrees. I kind of drew this. So the square root of 5 squared plus x squared equals the square root of 4 squared plus x plus square root 3 squared.
Okay, it's very good. Very good, very good. Yes.
Yeah, and then square root.
Right, you can solve for x. Yes.
Yeah. Square.
So x equal to square root 3. Okay.
Yeah, I got x equals square root 3. So yeah.
Let's solve this. Okay, so it's gonna be x squared plus 2x square root 3 plus 3 there. So therefore you get the x squared canceled, right? So then you get 9 minus 3 is 6 equal to 2x square root 3. So x equal to square root 3, okay? And then, so therefore this ratio is 1/2. This ratio is 1/2, okay? Very good, very, very good. Or you can do this. You see that your DE is what? DE is 3, yes? Because D to this point here called B prime is 5, yes? Because it's an equilateral triangle. Grace, I'm talking to you.
Yeah, I see.
Do you see that? Okay, so now you get this triangle, right? So you get this triangle. This is 3 here, right? And this angle is 30, yes? This is 30, right? And so you look at, so this is x. So this is x. Now this part is a 3/2, yes?
Yeah.
And now you use the 30, 60, 90 triangle here again, yes?
Yeah.
And you know that this one is 1/2 of x, yes? Because the opposite side is 1/2 of this hypotenuse. So therefore x equal to root 3, okay? So you can use this one. I mean, what you did is perfect fine, perfect fine.
Okay.
Yeah, it's very good. You are apparently you understand these right triangles, equilateral triangles, and 30, 60, 90 triangles. Very good. Any other solutions for this problem? Chris? Yeah, usually this is not the best way to do, but your method here is a perfect fine. So right now, I don't see other method is shorter than this, but this is yours is good. Okay, so William, what is your idea?
So my idea was to split the diagram into several figures, including a square and
Okay,
two
so
30
yeah, that's fine. You can do that way, but that's not the method I'm trying to teach the class. Okay, so you can try a lot of different ways, just like what Grace tried here. It's very good. You can try all kinds of ways, but usually there's a very standard method here. I want people to know. What is the method here? Anyone has a different thought on this? Matthew, what was your thought on this? Did you try this?
I just drew a line from D to AB as like a
D
perpendicular.
to AB? Oh, you draw this this one.
Yeah.
Okay, so you can do that, no problem. Okay, so I don't want you, but you see, any of those kind of method is not, you know, different from Grace's method. Okay, so what I can do is this. Usually, it's always the method you should think. Okay, so that is.
Is it you extend DC and AB and it will make a 60, 30, 90 right triangle?
Yeah, where do I extend? Which way?
Extend DC to the right and AB to the right.
Oh, I see. You are, yes, that's a perfect fine. Okay, so I could also do this because in this case, it's probably easier to do this way. Do you agree? Yes. No, I mean, the idea Edward talked about is a correct idea, but you could do in two different ways. So that's why this problem is good because there are a lot of options. Okay. You all see this?
Yeah.
Because it's a right triangle here, you see here. And therefore this is 30, okay? Yes? Are you with me? Yes, so you can see that this part would be 3 here, yes? Because this side is half of the hypotenuse, yes? But now this is a right triangle. So it's again 30, 60, and 90-degree triangle again, right? And therefore, you know, this side would be equal to what? So this side would be square root of 3 here. Then this is 2 root 3, okay? And therefore, you see the ratio. Are you with me on this?
Yes.
Okay. Now, even though we didn't say it, but you should know that if these were 30, 60, and a 90-degree here, then that means this is 1, this is 2. What is this side here? Tell me.
Square root 3.
Right? So that's why I have this. Agree? Are you with me on this? Okay. So this is the thing that you need to know. Is this correct? So you get yeah. So 3 plus 9 square root of this is a 2 root 3. Okay. This is correct. Yes. Okay. So this is the using the 30, 60, and the 90-degree triangle. And or you can use similar triangles here. Okay. What is your thought on this? You don't have touch screen. That's fine. You can just talk. I can draw it. You can join on your iPad. No problem. Yes. Yes. Okay. So you can rejoin it if you want to. Okay. So let's just see the other problems. Number 3, let a triangle ABC be an isosceles right triangle with a hypotenuse BC. Through a vertex A, let's draw a line L parallel to BC. Choose D on L be such that BD equal to BC. And DB intersect with AC at E, show that CD equal to CE. Did you guys Did you guys solve this problem or tried it? This is a hard problem. Say it again.
I did.
You did? Wow, cool. So what kind of picture you drew?
Actually, couldn't really like completely solve it, but I did draw like a diagram for it.
Okay, so let me draw the diagram for you. Okay, so first, so we have this. And we have 30. Oh, I mean, this is a isosceles triangle, right? Sorry. So it's going to be like this. So it's a 45, 45, 90-degree triangle here. And let's see, it's not too good. So why don't I have a good angle there? Okay, I should have something more horizontal. Okay, now you have a line L, right? Passing through this vertex. So this is A, B, and C. This is isosceles. And then which side your point D is? William.
In this case, D would be closer to the point C because in this case, BD would be equivalent to BC in length.
Well, actually, you can do this from both sides. So if you only did one side, it's not complete. You understand?
Yes.
You understand what I'm saying?
We need to like draw it on both sides.
Yeah, you could have a different one. So if you solved this one, you only did this problem for it's only 1/2. So this is right angle there, right? And so this point here is E here, right? And they want you to prove that is CD equal to CE, right? So how do I solve this?
So first we can recognize that since line L and BC are technically parallel, we can
Right.
find a lot of congruent angles.
True, yeah, but that's not the, yeah, true. So?
You can connect B to L with a perpendicular line.
Right.
And
Okay, hold on. Let me follow your suggestions. So we're going to draw this one, right?
yeah,
Is that what you're saying? Okay, so this is good. Yes. And so this is altitude. Yeah.
yeah, and you can let that point be G, and BAG is equal to 45
BAG is
degrees.
45. Yes. Oh, you mean the angle, right? Yes.
Yeah.
This is a 45. Hold on. Let's see why this is a 45. Yeah, because because this is 45, this is also 45. Agree?
Yeah.
Yeah, very good. Because the alternating interior angles here. So this is 45. So therefore you do have 45 there. Yes, go ahead.
And so BD equals BC, so angle BDC is equal angle BCD.
Yes.
And
Did you solve this? have you solved the problem or you just want
Yeah.
to try it? You solved it? Okay, good. I mean, this is a, okay, how many people solved it? William, did you solve this?
No.
Okay, Grace?
I don't think I managed to.
Yeah, so it's a very hard problem. And then who else? I said hard is hard to see. Okay, the problem is not hard, but it's hard to see. Okay, so how about Rebecca? Did you solve this problem?
I tried to, but I realized the picture was wrong. So
Yeah. Yes. Okay, so Edward, can you keep going?
Yeah.
I want to see if Matthew, did you solve this?
Yeah,
You
I
should.
saw.
Okay, very good. Let the young student try first. Okay. Okay. Yeah. Go ahead. Edward, yes.
So so I set DBC to X and
E, B, C to be X, right? So you want this angle to be X?
yeah.
Mhm.
So and then BDC would be 90 minus half of X.
Right, yes. So, okay, so it's a 90 minus half of X. Very good. And then this is C.
DCB is also that.
CB, yes, it's the same, yes.
And that means ECD is 45 minus half of X because you subtract 45.
Which one, DCE or it's a DCE, right?
Yeah,
You mean this angle?
yeah.
This angle here is 45 minus X over 2. Yes, very good.
And then angle E angle E angle EBEC is 180 minus
I don't see that. So which one you are talking about? Angle what?
BEC.
EEC. Yes, equal to 180 minus 45 minus X, right? So 135 minus X. Is that right?
Yeah, so DEC equals 45 plus X.
DEC, but those were clear, yes. So EC equal to 45 plus X.
So you can find X.
What is X? The
Oh.
whole thing is to find X, actually. If you find X, then you are done.
I forgot how I did it.
You are missing a point here. Okay, so the whole point is to find X, actually. No, you don't need to trace all these angles, but all those angles are pretty straightforward. Anyone else besides Matthew? Matthew, can you help us then?
Yeah, I can help.
Yeah, thank you.
So what I did is that I called AB the side ABX.
Yeah, you can write. Yes. Let me erase something for you. Let me erase something for you because we don't really need this angle chasing here. Okay. Sorry. Okay, so yes, go ahead. You can keep writing. You don't have to worry about me.
So so I did some angle tracing, but then I was able to I just wrote sides in terms of x. So then
Okay.
so I drew a perpendicular line from B to L as well.
Mhm.
So then that means since this is 45 degrees
Right.
and this is also 45 degrees,
Right.
these two sides are equal. And then if we just, that would just be root 2 over 2 times x. And then since also triangle ABC is also an isosceles triangle, this side length is just root 2 of x.
You can use x equal to 1, for example, right?
Yeah, it's just without loss of generality.
Mhm.
So then that since BC is equal to BD, this side is also square root 2 of x. And then if you notice here, you can see that triangle BGD is a 30, 60, 90 degree triangle. So then this side would be 30 degrees. And then this angle here would be 60 degrees. And
So
then
hold on. So you mean this one? You mean the BDG?
yeah, triangle BDG is a 30, 60, 90.
Ah, that's very good. Yes. So because the hypotenuse this is the hypotenuse, right? Oh, sorry.
Yeah.
Yeah. So this is the hypotenuse here, and this is a half of that. Yes.
Yeah.
Yeah, that's a good observation. Yes, very good. Yes, very good. Edward, do you see this? So once you have that, then you have this 30 degree here, right?
Yeah, 30
Rest
degrees.
is just, you use
Angle.
Edward's angle chasing, then you get this is what?
And then you get angle.
This is also 30 degree, yes?
Angle
Yeah.
D which is equal
So,
to 75 degrees.
right. Very good, very good. Good job. So this is just by observation that you have such a right triangle, 30, 60, 90 degree triangle there. Or you could do this way without doing any calculation here. Okay. So let's erase this. Instead of drawing it here, and you all get the right point here. Okay, so you get you find this you find this thing here, right? You draw from B to the parallel line there. You could do this way. You could just draw the true altitude here. Yes. You agree? So you draw the true altitude here. All right, so why do I draw this altitude? Well, because the bottom here, because this equilateral triangle, so this side equal to this side, agree? These two sides are the same, yes?
Yeah.
Yes, so these two sides are equal, okay? And if you call, let me draw a point. Yeah, so let me draw this, let me call this point as G here, right? So this is half of that. Now that's called this point BF, yes? So DF equal to what? Equal to AG, yes? Because both were altitude, yes? But remember that this is the midpoint of the hypotenuse of the right triangle. So this says GA equal to GB equal to GC, yes? Are you with me? We are using
Yeah.
first Factor says that the midpoint of the hypotenuse is equidistant from the 3 vertices. Yes. So GA equal to this. And but GC is just half of what? BC, yes? But that's half of BD, yes? You agree? So what does that mean? That means this triangle here, this is a triangle BFD is a 30,
60, 90.
60, 90 triangle, yes? And therefore, this angle is a 30 degree, yes? That's how you prove it. So once you solve this angle, the rest is pretty straightforward. You all agree? Your Matthew's proof is very computational. And he just noticed that in essence, it's essentially the same. But what we want you to see here is that we have the right triangle property here. The midpoint of hypotenuse is equidistant to all these 3 points, 3 vertices. That's the one you want to always use it, right? And you could do this. Okay, so this is number 3. 1 second. Number 3, number 4. Let's see, number 4. What is number 4? Number 4 says triangle ABC is an isosceles triangle. AB equal to AC. If the altitude from A to BC is 1/2 of BC, what is the measure of a triangle BAC? What is that? Did anyone try this? It's a really trivial problem.
I did.
What's the
I
angle?
solved it.
What's the angle?
So first you draw ABC.
No. What's the angle? I just need the answer. Because that problem is a really trivial problem. Right? So you know that the problem says AB equal to AC. AC here. And if the altitude is 1/2 of BC, H is 1/2 BC. What does that mean? And then you see these 2 are equal, right? So that means these 3 sides are equal. That means what?
That means it's 90 degrees.
Yeah. So in other words, this is you have a circle here, right? Because the circle will pass through these points, and then this would be the center. Agree? This center BC must be diagonal, must be the diameter, and so therefore this must be 90 degrees by inspired angle theorem. Yes? Yes, that's the correct answer. Okay. Now I see. Sorry, I didn't want to erase this. Okay, Matthew. I said earlier that for this number 3, you should have what? Have a different cases, right? What is the other case?
Well, like,
You solve the
but it said it intersects AC at E. If you draw D on the other side, it won't intersect AC.
other one case, right? Different case is this case. So this one, I really need you to do it as an exercise. All right, so you could have this, you could have something here. Like this, right? So these sides are equal. You agree? And then the thing is that you should be able to, E is here. This is a D. Yes?
Yeah.
So prove this again. I guess most of you did not do this, right? You didn't do this case, right? So this is case 2. Can I leave this as a good exercise for you guys? Right?
Sure.
Okay.
This is a homework assignment one more time, okay? Yeah, you solve the one case, but not the other. So the other case, the one case we solved it, we use 2 different methods, but essentially they are the same idea. But for the case 2, see if you can solve this yourself, okay? So make sure when you do geometry, you have to discuss all cases. You cannot just do one case ignoring the other case. Then your solution is incomplete. If you go to USMO or JUSMO, you only get like 3 points, probably half of the points, okay? Not half, 3 points, not even half. So 3 out of 7. All right, so this is number 3, and then number 4 we just did. Number 5, did anyone try number 5?
I did number 5.
We did number 5, okay, so, but the number 5, the second statement is incorrect,
Yeah, I think you meant to do 1 over BC squared.
That's right,
instead of-
yes, very good, very good. Yeah, it's a 1 over BC squared, not 1 over BD squared. It's a typo, and because I was just doing all these things, so this should be BD squared. Okay, so number 5. Let me correct it. So you get. I will do the correction next time. All right. I'll do the correction next time. I will send you different notes. So I want to leave this to everybody so that people can have a chance to try it.
Oh, okay.
Yeah, can you? Yeah, so I want to keep going for the more geometric theorems. The problems which I left out, we have a total 10 problems, which are, we did 4 of those, right? We did 4 of those. Let's say number 5 is a projection theorem on the right triangles. Do you guys still remember the theorem on the projection theorem?
Yeah.
Yeah.
Number 6, it's again projection theorem, agree?
Yeah.
Which can be done pretty nicely and quickly, okay? If you use similar triangles, it's gonna take a while for you to get it. Number 7, do you guys know these racial relations? Do you all know them?
Yes.
Yeah.
You do?
Like.
Okay, so make sure you can prove them, okay? So number 8 is hard. 2 implies 3. Last time we proved the 1 implies 2, and then we proved the 3 implies 1. And you need to do 2 implies 3. Number 9 is just angle chasing, right? So last time we proved that for number 9, you need a circle. You need A, B, C, D on the circle to prove that the angle A plus angle B plus angle C all the way to angle E equal to 180 degrees. But it's actually true for any stars there, okay? For the number, for the second part, they have A, B, C, D, E, F, G, A, B, C, D. Oh, I miss an angle there, right? So there's an E, there's an F, okay? So you need to add those. I will make corrections when I try to make up the homework again. Number 10, let's start with number 10 today. Okay, so number 10 says the following, that suppose you have a circle and you have 2 chords there, A, B, and C, D. Now the theorem says this is A, B, this is C, D, and the intersection is P. The theorem says this implies that the triangle PAD is similar to triangle PCB. Can you prove this?
Yes.
Yeah.
Trivial, right? So why is it trivial? Tell me.
What does
Because
trivial
this
mean?
Trivial means that it's on the nose. Is the problem on the nose? Is the statement on the nose?
Yeah.
Because this angle equal to what?
DCB.
PBC.
Yeah. Not DBC, right? DCB, right? Because
Oh.
inscribed angle, you see both subtend to the same arc.
BC. I mean arc BD.
Yeah. So therefore, these two angles are same. So obviously these are similar. Do you agree?
Yeah.
You know what this similarity give you? Well, since it's trivial because since the angle PAD equal to the angle PCB, okay? And you also have the vertex angle at the P. So therefore these two are similar. So this is true. That's why it's a trivial. Now, because once you know they are similar, you see what you get. You get a PA over PC equal to PD over PB, okay? And that's also equal to AD over CB, yes? By similarity, right?
Yeah.
Now, by similarity, we have this equality. We ignore this part here, which you shouldn't. That is, you just look at this one, you get what? You get a PA times PB equal to what? PC times
PD.
PD, which means this product always is the same. Do you agree?
Yeah.
So if you start with any point in the circle, pick any point in the circle, inside of circle, you draw any two chord, then this ratio is always the same. So in other words, if you draw one more, they should also be what? This product should also be the same. Do you agree?
Yes.
So if you draw another one, PE and F, then this should also be equal to PE times what? PF, right? So this tells you, sorry, there's a siren there. Okay, this tells you what? So here is the definition. Yes. The definition is this: the power of a point P in a circle, in a circle, all right? Sorry, it's hard to write in the circle here. Is PA times PB for any chord, okay, for any chord AB passes through the point P. That's because it doesn't depend on the chord chosen, right? You understand? And the theorem is the PowerPoint theorem. That is the power. So we denote this power as a power of P, okay? So the power of P with respect to this circle, let me use a shorthand here. With respect to the circle is what? Is independent of the chord chosen, okay? So in other words, you can choose any chord to compute this power. Does that make sense to you? Hello, does that make sense to you?
Yeah.
Yeah. The Rebecca, do you understand the theorem?
Yeah.
I don't need to prove it again. Do you agree?
Mm-hmm.
Because this is the reason. Yes. Using the similar triangles, you see that the PA times PP is always equal to PC times BD, no matter which chord you pick. Okay. So therefore, the power of this point here is well defined. It doesn't matter which chord you pick, okay? Now, there is a special chord here you can pick. The special chord, which chord is special?
The
William?
diameter.
Yes, the diameter, very good. Let's pick a diameter here. So in particular, let me call the E and F. So in particular, we can pick what? Let me just say this. The power point of P is equal to the R square minus the distance from P to the center square. So this is the center here, and this is the D here. So this is the complete theorem of the power point. Okay, so you we already done the first part of the proof, so we need the second part. So let's prove the second part only, okay? How do I prove the second part? Edward, can you help? The point piece here. So proof of the second part. That the power point.
I don't know.
Dr. G, I can't hear you really well.
I'm sorry. I don't see any problem.
Dr. G, I think you're lagging.
I think it's lagging a lot.
All right, so let's see. Can you hear me now?
Yeah, there were just like some moments where
Yeah.
it was just
Yeah,
silent.
sometime, yes. So the power point, we prove the second part, okay? What is power point P? It's equal to PE, so we choose EF, a diameter that passes what? That passes through the point P, okay? Then we have the power point equal to PE times what? Oh, yeah, PE times PF, do you agree? What is PE in terms of radius? So PE is the radius minus the distance P to O, okay? And PF is the radius plus the distance from P to O, okay? And therefore it's R square minus PO square. And PO is just the distance from P to O. You get it?
Yeah.
So in words, the power point is what? Is equal to PA times PB. And you can, if you choose a chord, it's also equal to this one, right? So this is a very, very cute theorem. For example, you could have an example like this, right? Without this theorem, to prove the theorem, it's kind of hard, right? To solve this problem, it could be hard. So let's say this is the center over here. So find the distance from P to O, to the center. Okay, so here, let's say we have a plot here. This is a 3. This is 7. Maybe a little bit shorter here. So this is a 3, this is a 5, okay? And let's give a radius. So the radius here is maybe 4 here, okay? So if you just given this data, find the distance from P to O, it doesn't sound like possible, do you agree? Actually, it does. I mean, if you draw some auxiliary lines, but this problem looks like they are all disconnected, right? Okay, so the solution is very quick because the 3 times 5 is a powerful point, agree?
Yeah.
And the power point P is also equal to what? Equal to R squared minus PO squared, do you agree? And you can see that PO squared equal to 15 plus 16. So therefore PO equal to square root of 31, do you agree? You see that this is a very effective method here. Even though you can eventually solve it by using similar triangles. But the point is that if you do not understand this theorem here, do not observe this theorem, then it's going to take a while for you to trace it. You agree? To trace through this theorem.
Dr.
Yeah.
Shouldn't PO be 1?
I'm sorry?
Shouldn't PO be 1?
I'm sorry. Did I make this wrong? Oh, I see. Sorry. Sorry. I'm sorry. That's right. So it's going to be 16 minus 15. Yes, it's 1 there. So therefore, PO equal to 1. Very sorry. I was jumping too fast. Okay. Okay. So do we all understand this? Yes.
Yes.
So, but you might say, what if the point is not inside of the circle, right? Okay. So if you have a circle here, and you have a point outside of it. So let's say the circle has a center O there. Can we define power point then? Well, certainly I can try, right? Let's just draw any line, which is secant line, passing through the point P. The secant line has 2 intersections with the circle P and A. So here's the definition of power point if the power is outside.
PA times PB.
Yes, very good. Yes, that's exactly what we would do. PA times PP, just like pretend if it's inside, right? Again. Now the question is that if you define this, there's a problem, right? Why it's well defined? You agree? Well defined means that what if you choose a different what? What if you choose a different what? What if you choose A? Sorry, I want to use a line there. What if you choose a different secant line? Yes. So here's the theorem. The power, so this is for any secant line. Okay. PAB. This is single line there. Okay, so the power of P is well defined, which means i.e. that it is independent of the choice of the secant line. Okay. All right, let's prove this. Yeah, how do I prove this? Again, we need the similar triangles, yes? You could construct differently, but if you just do this one and this one, you see what happens? Since angle ABC is equal to what?
Angle ADC.
So triangle PBC this angle equal to this angle, and this angle is you don't see this? Similar? PDA, do you agree?
Oh,
Yes.
I thought
All we
it
do is-
was.
Yeah, you were
congruent.
thinking something else, but this is on the nose, right? The angle P is shared, okay? All right, so this tells you what? You get PB over PA equal to PC over PC, no, PB over PD, right? So PD, and PC over PA, yes? And this tells you PA times PB equal to PC times PD. And therefore, we prove it's independent. Do you agree?
Yeah.
All right, so this is very useful, as you can see. Okay. But there is a special secant line. What is that secant line?
Tangent line.
Actually, two. I'm talking about secant line, not the tangent line. Tangent line is not the secant. So one passing through the center. Do you agree? Hello, are you with me?
Yeah.
So why it doesn't change this rotation here? So this is the one you have an extra secant line which is passing through the center. Okay, now if let's say PEF, if PEF passes the center O, right? Then you see that then you get the powerful point is equal to PE times what? PF, right? Now, if this is the radius we use here, you can see PE equal to PO minus radius. And PF is PO plus the radius. So therefore, you get PO square minus R square. Do you agree?
Yeah.
So we do have a second part of the theorem. That is, moreover, P power of P is equal to PA times PB. And it's also equal to PO square minus R square. Agree? Agree? So this is the second part of the theorem. So therefore, the powerful point has two different segments. One is inside, one is outside. Okay. And for the outside ones, these difference of squares from P to the center and the radius squared is a little different. There, in this case, it's a PO square. Sorry. In the previous case, we had so recall, if P is inside the circle, then we have the powerful point equal to R square minus PO square, agree? So don't forget that, agree? All right. Now, also we have one more thing there. That is, you can see that I can do this. You see, I can choose the chord here, the second line like this. I can keep what, making this second line closer and closer to what?
The tangent.
To the tangent, right? Eventually, you could have a tangent line there. So let me call this point here as T here. Okay. So if you just keep making this is B1, A1, this is B2, A2. And you can see that the powerful point P is equal to PA times PB equal to PA1 times PB1 is equal to PN times PBN, right? With the AN and BN both converge to what? Getting closer and closer to? To what?
The tangent PT.
To the tangent point, okay? Because if this second line is closer and closer to the, to the point, to getting closer and closer to the edge of the circle, you can see they both have to converge to the tangent point, okay? And this tells you, you can see that eventually this should converge to PT times PT, okay?
Yeah.
Because this is continuously moving, therefore it's PT square. I should say this is the limit, PT square, okay? But because it's continuous moving, so this picture is continuous moving, right? Never change. So therefore PT square should be equal to the powerful point. So this is the third part of the theorem, that is, moreover, this 2n is equal to PT square. To prove exact equal to this, we have to do an additional argument here. So we want to prove this additionally. Give me 1 second, okay? So give me 1 second here. So let's prove the last part of the theorem. That is, we still need the so I still need this. Okay. First of all, we have this tangent line there. So this point here is T. And then we also have, we have A and B. So this is the center O here. So we need to prove this, right? So proof of a power of P equal to PT squared. How do I prove this? Matthew, you know how to prove this, right?
Do we just draw the chord AT?
Say it again. Chord AT. Yes.
And then would you just draw B to T?
B to T. Okay. Well, let's draw one more. P T passing through the center. Why do I draw this? You know the property of tangent line, right? Tangent line says what?
Perpendicular to the diameter.
Yes, okay. You have a right angle there. Yes. So because of the right angle, so you see this angle here, it's called the tangent chord angle, right? So tangent chord angle is by definition the PTA. That's a tangent chord. Degree, this is angle. Let me call this angle as alpha here, right? Right. So we let this be the alpha. Because it's a right angle, so what is this angle then? So this implies the angle let me call this as a B, the D here. ATD equal to what? Equal to 90 degree minus alpha degree. Hello?
Yeah.
It's just, you know, because that angle is a right angle. And if you look at this AD here, here's what happens. Says TD is a diameter, right? The angle TAD equal to what?
90.
90. So it's equal to 90 degrees, yes? So that means because it's a 90 degree, so this is a 90 degree. So that tells you this is also alpha, do you agree? So this says the angle TDA is equal to alpha again, yes?
Yeah.
Because these two angles must be, this angle and this angle must be complementary, yes? So it's alpha
Yeah.
again. But then by inscribed angle theorem, this angle is also what? Alpha, okay? So this implies that TBA or P is equal to alpha as well. Yes?
Okay.
You agree? So this implies the triangle PTA is similar to triangle PBT, agree?
P. Yeah.
Because the alpha angle must be matched. So this implies that PT over PB equal to PA over PT. That implies that PA times PB equal to PT squared, which is equal to the power of this point. Okay? Yes. So this one actually has a corollary in the proof. That is the tangent chord angle equal to the inscribed angle. Agree? Is congruent to inscribed angle. right? Subtend to the same arc, right? Subtend by the same arc. So you see here, this angle here, this is the tangent chord angle. Do you agree? So this is tangent, this is a chord, okay? Tangent, and this is a chord. You agree? And this one is what? The inscribed angle. So tangent chord is subtend by this arc, as you can see. Yes? Are you with me?
Yeah.
Yeah.
So this is the theorem. So this is an important theorem called the tangent chord angle equal to the inscribed angle theorem. Make sense? All right. So we are done with this theorem. It's called tangent chord theorem, tangent chord angle theorem, and the powerful point. All right. So powerful point is a very, very useful theorem in the math Olympiads because it's a quicker. You can avoid you to reconstruct the similar triangles. Okay, you get the ratio, you get these relations right away. All right. So so it's a very powerful theorem. So that's all I can do today. Actually, I don't have that much. Let's see what else I can tell. So I'm done section. I mean number 5 and number 6. All right. So next time we're going to discuss consecutivity. That's a very powerful topic in Math Olympiads. You have to, we're going to do that from scratch. So you will understand it completely. All right. So, and that's all for today. And you should keep working on the homework. I'll give you additional problems for practice. All right. So you need to finish all the problems which you didn't try. And even if you listen to, you saw some of the proofs today, you should go over those yourself one more time. Okay, so it's a non-trivial to do well in this course. All right, so even though it doesn't involve that much algebra, but the geometric argument is very sophisticated. Okay, so make sure you spend time on this. If you do not spend time on this course, for like 4 or 5 lectures, you're gonna get lost very quickly. Okay, you won't be able to catch up with other people. Okay, so I do see several students are following the class very well. All right, so let's stop here, and I'll see you next week. We keep this schedule. All right, so have a good day. Bye bye.
Bye. Thank you.
Thanks.
Thank
Bye.
you.
Thank you.